Assalamualaikum. Good morning, everyone.
Assalamualaikum.
Can you hear me? Can you hear me?
Boleh tu.
Okay. So, we move to section 3.4, modeling of translational mechanical system. Okay. The concept still the same according to the chapter 2B that I WhatsApp to you a few days ago. Okay. We are still using the force displacement formula, which is for spring, F is equal to kxt. For damper, F is equal to b dx dt. And for the mass is F is equal to m accelerations, okay, of the displacement. So in chapter 2, we are using k, f, vs, and ms square. But for the time domain, we are not using this anymore. So we are using the T domain formula. Okay. Similar to the rotational system as well, where we have a torque and angular displacement, okay, which is the T and theta T. And the formula that under consideration is the torque equal to K theta T, torque equal to damper, angular velocity, and torque equal to J angular accelerations. Okay, so we are not using this anymore. So let us see a simple modeling. Okay, simple modeling that using translational mechanical networks. Okay, by looking at this, we have a single damper, single spring, and single mass. So the input of the system is Ft, and the output of the system is Xt, the displacement. So to model the system using a state space approach, we have to define the state variables. Okay, which is defined as xt and dx dt. So since x already used as a notation for displacement, and similar to x dot t as well, so we can choose other letter instead of x. So in this case, we are using z. Okay, so state state vector is z1 and z2 stands for the state variables 1 and state variables 2. Okay, so we can use other letters if you want, but most of the book using z or z for the translational mechanical system. So the system is a second order system as we proved in chapter 2b. Okay, is a second order system. So we define the state variable z1 is equal to x displacement, and z2 is equal to dx dt, which is the velocity. in this case is a dz1 dt, or simply known as x dot or z dot. Okay, so if we differentiate dz2 dt, so it will become accelerations, okay, d square xt and dt square, as shown here. Okay, so for the state variables is given by z1 and z2, and derivative state variables is z1 dot and z2 dot. Okay, z1 dot is uh, x dot, which is equal to z2. Okay, so we already have the first state equation, and z2 dot, the second derivative state vector, is x double dot. Okay, so this one you have to derive. Okay, you have to derive this in order to find the second state equation, and in order to derive the z2 dot or x double dot, we have to use the free body diagram, which is shown here. So f of t, okay, is the force, the input. X of t is the displacement, the output. Okay, so when we give a force on the right hand side, automatically this is the action. Okay, the action. And in the same time, there is three force as a reaction. Okay, reaction, which is due to the spring K, due to the damper FV, and due to the mass, which is M. Okay, three reaction force and single action force. Okay, and this is in the time domain, and is in the Laplace domain, is shown here as we did in the chapter 2b. Okay, so now from our understanding from the free body diagram, okay, we can construct the differential equation of motion. Okay, differential equation of motion as shown, right? Where Ft, the force on the right hand side, equal to the reaction force from the spring, from the damper, and from the mass. Okay, and our concern, our interest is to find the x double dot, okay, or known as d square x dt square. So therefore, we already find it here. Okay, so we make this x double dot as the title of the equations and bring m to the right. Okay, bring m to the right, so it will become minus k over m xt minus fv over m x dot t and plus 1 over m. So in your notes, you have to insert the minus. Okay, the minus loss during conversion from the PowerPoint to the PDF. Okay, can you get it? Can you see it? Hello?
Dalam nota ada tolak, ada minus tu.
Macam mana okay, saya tengok screen lain kot. Okay, apa? Right. So we rearrange the equation since the first state. This is the second state equation. So the first state equation is here. Okay, z dot is equal to z2, and this one z2 dot, sorry, z2 dot, okay, equal to x double dot. So this one is the x1, z1. This one is the z2, and this one is u. Okay, so that's why you will get the second state equation. Okay, and the output, okay, as we mentioned just now, is the displacement. So y is equal to xt equal to z1. So rearrange 3, 4, and 5 into matrix form. Okay, which is z dot, z1 dot, and z2 dot. Okay, so this is matrix E. This one is a state vector. This one is the derivative state vector. This is the matrix B, input, output, matrix C, and the state vector as well. So it is a second order system, as proved in chapter 2B. So in chapter 2B, the transfer function model is 1 over m s square plus FVS plus K. This is what we derived in chapter 2B. In chapter 3, the model is not in frequency domain, but in time domain. Okay, time domain. So we get the two-state equation and one output equation as shown in the slide number 81. Okay. Abad, Muhammad Abad, Muhammad Abad, not coming. Shukri, Shukri, not coming. Ikhwan,
Yes, okay.
do you understand?
Yes.
Huh? Do you understand? What is the difference between state space representation and transfer function modeling? Ikhwan, Ikhwan, tak datang. Ryan, Ibrahim,
Yes, doctor.
Ryan,
Yes.
what is the difference between state space representation and transfer function modeling?
Sorry, doctor, I'm not sure.
Huh?
Sorry, doctor, I'm not sure.
Hian Yong,
Yes, doctor.
what is the difference between state space modeling and transfer function modeling?
Uh,
You look at the slide number 81. Tahu. Lutung, Lutung.
Yes, doctor.
What is the difference between state space modeling and transfer function modeling?
Uh, Transfer function is for single input and single output. State space is for can use for multiple input and multiple output.
Not really. Pang Yi Heng,
Yes, doctor.
Same question.
For my understanding is both we can get the same equation in the diagram B there.
Okay, as I wrote there, the difference between state space modeling and transfer function modeling. Transfer function modeling is in fraction form, while state space modeling in matrices form with first order differential equation. This is the first order differential equation. Next, slide number 82. Example 3.8. When force Ft acts on mass M1, yeah, move to the position x1 while system mass 2, okay, move to the position x2. Find the state space representation of the system using x1, x2, and their first derivative as a state variable. Let x2 be the output. So Ft is the force input, and x2 is the displacement of M2, okay, as the output. So now we are going to understand what is the word here. Find the state function if the state variable is x1, x2, and their first derivatives as the state variables. Suhada? Suhada?
Yes, doctor.
What do you understand by this word? x1, x2, and their first derivative as the state variables.
The state variable is x1, x2.
Then their first derivative? Apa maksudnya?
Um, Same as state variable.
Alah. So the meaning of this word is x1t, x2t, x dot t, and x2t is the state variables, meaning that you have four state variables. Okay. So in this case, what I did is z1 is equal to x1. Then find the derivative z1 dot, which is equal to x1 dot equal to z2. Equation number 1. z2 is equal to x1 dot. z2 dot is equal to x1 double dot. This one we have to derive. Okay. Equation number 2. z3 is equal to x2. z3 dot is equal to x2 dot and equal to z4 is the second state equation. And z4 is equal to x2 dot, z4 dot is equal to x2 double dot. Which one you have to derive? Derive meaning from the free body diagram. Okay. So as I mentioned just now, the input is u, the output is y. Okay, which is correspond to the force and the displacement of x2. So now we draw the free body diagram. Okay, so by looking at the M1, this one is M1. Okay, full M2. This one is for M2, full M1. M1 moving. M2. Okay. So we hold M2, the mesh number 2, hold, not moving, and then we assume that M1 is moving. And the force involved on M1 is shown here. So Ft is the force to the right as mentioned here, there, okay? And as you can see that between M1 and M2, there is a damper connected. So this damper connected have a relation with the X1 and with the X2. So it is can be related that there is a force due to the X2. Okay, so that's why there is a force which is parallel or same direction with the force Ft, which is Fv x2 dot, which is the damper in between mass 1 and mass 2. And as usual, spring, mass and damper is the reaction of the force given to M1. Okay, Ft is the action, and K1, M1, and Fb is the reaction. Okay. So therefore, from the free body diagram, we construct the force, which is the total force on the right equal to the total force on the left. Okay, as shown there. So Ft is equal to M1 x1 double dot Fv x1 dot plus Q1 xt. And this one actually from the left, okay? Originally from the left. So since we want Ft is the title of the formula, so we move the damper force to the right and it becomes negative. Okay. So we combine the Fv of the damper between x1 dot and x2 dot. As you see in my notes, okay, when you have a damper connected to the mass 1 and x2 without any reference or datum, so it is the difference between x1 dot and x2 dot using the same damper. That is for the M1. For the M2, so whole M1, M2 is moving, assume. If we don't have assumption, so we cannot derive this formula. So for M2, when there is a force, okay, towards the right, so there is a damper, okay, Fv x1 dot due to the x1, okay. And then reaction 3, which is spring, mass, and damper. And from there, we construct the second differential equation for mass M2. Originally, this one is from the left. When we move to the right, it will become negative. So now we have the x1 dot, which is here. We already have two state equation, which is z1 dot and z3 dot, which is equal to z2, z4 from the beginning here. Okay, equation number 1, equation number 3. We already have two state equation. So we have to find the x1 double dot and x2 double dot from the free body diagram and from the differential equation that we construct from the free body diagram. Okay, so therefore we make x1 dot as the formula title. Okay, then we move all associate with x1 dot to the right. So this one will be x1 dot will be what? X1 dot. X1 dot. X1 dot is Z2. x2 dot is z4. Okay, and x1 and the input. Okay, so that's why you see this equation number 3, state equation number 2, and then x2 dot is minus fvm2 x2 dot, which is z4, x1 dot, which is z2, and x2, which is z1. Okay, sorry, z3. So now we already have the 4 state equations. Okay, so this one already have. So rearrange 1 and 4. 1 and 4. Okay, so you can see that we have 4 derivative state variables, 4 state variables. Okay, and matrix A, B, and C. Okay, so it's a 4 by 4. 4 by 4. Uzair, Muhammad Uzair, what can you see? What can you see on the slide 86? What is the system order?
4.
Why?
Sebab dia because 4 state variable.
4 state variables. Okay. What is the size of matrix A, Uzair?
4 by 4.
So 4 by 4. Matrix B, size?
4 by 1.
4 by
1.
4 by 1. Matrix C?
1 by 4.
Okay. Faham eh?
Faham tak saya?
Zin,
Ya, saya kata.
baca soalan. Slide 87.
Boleh kata. Example 3.9. Find the state space representation of the system. X1t and X2t is the output and Ft is the input of the system. X1t, X2t and their derivatives are the state variable of the system.
So, apakah state variables-nya?
State variable dia adalah S1t, X2t and dia punya derivative lah. Kita differentiate S1t and S2t.
How many state variables?
4.
4. Okay. So displacement x1 is the first state variables. Displacement x2 is the second state variables. Acceleration of mass 1 is x1 dot, third state variable, and x2 dot, which is the acceleration of mass 2, is the fourth state variables. And our target is to find z1 dot, z2 dot, z3 dot, and z4 dot. Ainul, Syamila,
Ya saya
kau kat mana?
kat rumah.
Ha? Kat mana?
Dekat rumah.
Rumah mana? Where's your house?
Keluar.
Okay. What is the first derivative state vector? Slide 87.
Apa nak?
What is the first state variables, derivative state variables?
Derivative.
Slide 87.
X.
X1. X1 dot equal to Z. 3. I don't lambat. Amirul? Amirul? Tak datang.
Hello.
Amirul. Second state variables. Z2 dot.
Hello.
Kita planet lain. Oh, tak apa. Hafiz. Z2 dot.
X2 dot.
X2 dot. Ni. Z2 dot. X2 dot kan? Equal to.
Z4.
Oh, Z4. Z3 dot. Hafiz.
Z3 X1 dot.
Dot. Z4 dot.
X2 double.
Dot. So kita nak cari yang ni lah. Output yang biasa is X2. X1 and X2. X1 plus X2, the output is a total of two displacement. Yeah. So solution. Okay. Ini jawapannya. Ini is the answer. I think this one is examples in the notes, chapter 2B. This is the answer. Transfer function. Okay. But this in the transfer function, the output is only one. Okay. So what I did is I derived the state space representation using, four state variables. X1 dot and X2 dot and their derivative are the state variables. Input is force, output is X1 plus X2. Displacement is X1 and X2. So as usual, draw the free body diagram. Very important, you draw the free body diagram. Do not skip. Okay. So this is the way I did force on M1 due only to the motion of M1. Force on M1 due to the only motion of M2 and all forces. So in this case, M2 whole. In this case, M1 whole. Okay. So with that, you can get the total force on M1, similar to the M2 as well. Force on M2 due to the only motion of M2, whole M1. This one is whole M2. Okay. Then you replace all the value of the mass, of the spring, and of the damper constant. For mass, the unit is 1 kilogram. For the spring constant, the unit is Newton per meter. So in this case is 1. For the damper, we have 3 damper, including the friction, which is 1 Newton second per meter. Unit is Newton second per meter. We have 3 dampers, guys. One is the in between M1 and M2 and friction. Okay. Friction. So if the question asks you, ignore the friction or frictionless. So you can assume that FV1, FV2 equal to 0. Okay. But in this case, friction is taken into account in the building, in the build-up of the model. So we derive the derivative state vector which is z1 dot, z2 dot, z3 dot, and z4 dot. In definitions is velocity, x2, acceleration x1, and acceleration x2. Okay. Then we write the state variable as z1, z2, z3, and then these matrices. And then there is a t there. What is
So hopefully you have some ideas how to collaboration and how
veteran?
team work
Veteran?
Yes, Doctor.
not different setup, but
Veteran?
we can get to
Yes, Doctor.
Noise.
status of the patient.
Oh, sorry, Doctor.
Veteran? Okay, Amir, Muhammad Amir. Muhammad Amir.
Yes.
Muhammad Amir.
Yes. I hear you.
What is T in this slide 92? Power of T.
Transpose.
Transpose.
Yes.
What is transpose? Meaning?
Make the row as make tables as rows and rows.
What is that? I don't understand.
Flip the matrix.
Flip, eh? How you flip? How you flip? You interchange of row to column, column to row. Interchange, the keyword. Huh?
Okay.
Interchange. Amir,
Yes.
where you come from?
I'm from Sudan.
Okay. Have you been to KL?
Yes, one time.
One time. Have you ride the LRT?
Yes.
Have you heard about interchange?
No.
Change. You want to change LRT to MRT, MRT to other vehicles, so you go to the interchange station. That is the concept of interchange, row to column. Change the row to column, okay? So now is the solution where you combine everything to build up the x1 double dot, which is over here. This is the x1 double dot. And then you replace with the corresponding state variables, z1, z2, z3, z4, and the input. And this is the equation number 3, because we already have z1 dot equal to z2, z2 dot equal to z4. So this is equation number 1, this is equation number 2, this is equation number 3, and finally we get the equation number 4, okay, for the state variables. And we rearrange, so you will get the matrix A, B, and C, okay, accordingly. And this is the model state space for the translational mechanical system, mass, spring, and damper. Okay. Another example here. Okay. I ask Saifuddin. Saifuddin, are you coming?
Yes, sir.
Okay, read the questions.
Determine the state space representation of the mechanical system below if the state variables are depicted below. The t equal to x1t, x2t, x1 dot t, x2 dot t transpose.
Okay. And the constant?
The constant m1 equals to 2500 kg, m2 equal 320 kg, k1 equals to 80000 Newton meter, K2 equal to 500,000 Newton meter.
500,000.
Okay, okay. FV1 equals to 350.
Allah. Okay, thank you.
Okay.
Shukran, Habibi. Shukran.
Okay.
Okay,
Thank
okay. So as usual, now the constant of the mass is the real constant. Okay, 2,500 kilogram, 320 kilogram. K1 80,000 Newton per meter, 500,000 Newton per meter. FV1 350 Newton second per meter, and FV2 is the 5020 Newton second per meter. All are located here. Okay. This is a bus suspension system. Okay. This is the bus suspension system. Okay. So as usual, you draw the free body diagram. Okay. And then from there you have 3 versus 3. Okay. And this one 2 versus 1, 2, 3, 5. Okay. Forces. Okay. So state variables mentioned there. The state variables is here. So do not use X, use Z. Z, Z1, X1, Z2, X2, Z1, X1 dot, Z2, X2 dot, Z4, X2 dot. Okay. And we want to find the derivative state variables, which is Z1 dot 3, Z2 dot Z4, Z3 dot X1 dot, and Z4 dot X2 dot. This one we have to derive from the free body diagram. Okay. And from free body diagram, we can write the equation. Okay. The differential equation for the force. Okay. As shown here. Okay. Then we insert the value of constant. Okay. Insert the value of constant and then simplify. So you get equation number 2 for Z3 dot. Okay. So Z1 dot we already have. Z2 dot we already have. So now Z3 dot is already done. And the final one is the Z4 dot. Is equation number 4. Okay. From there, the output is Z1 is equal to X1. So we get the state space representation as shown here. If the output is, if the output is Z1 plus Z2, okay, meaning that is the total of displacement X1 and X2. So this one will be 1, 1, 0, 0. That's it. Okay. In this case, we mentioned that X1 is the output, but if the question said the total displacement is the output, so X1 plus X2. So 1, 1, 0, 0 is the matrix C. Okay, so other examples is shown here. Okay, you can read by yourself. So this one is a 3 degree of freedoms. Okay, with X1, X2, and X3 dot. Sorry, X3 is the what do you call that as the displacement. So Z1, Z2, Z3, and derivative Z4, Z5, Z6. Okay. So this one is X1, this one is X2, this one is X3, X1 dot, X2 dot, X3 dot. Okay. So if you want to find the derivative state vector, X1 dot, which is Z4, Z5, Z6, Z1 dot, pseudo. Okay, as shown here. Okay, use the same concept of free body diagram. Write the equation of motions. Okay, and replace with the corresponding K, M, and FV. All are unity. Okay, then you will get 6 by 6 metric system. Okay, 6. Okay. D. Okay, so that's all for today. First Lisa. First Lisa, how are you?
Fine.
What is the order of this system? Slide 105.
6.
Why?
6 state variables.
6
State variables.
state variables. Okay. Hatim. Hatim,
Yes, doctor.
if the output is x1 plus x2 plus x3, what is the output equations?
For this, doktor yang ni, dia punya cell S1, S.1 kan? So, 1, 1, 0, 1, 0, 1, 0.
1 0 1 0 1 0. Okay. Betul.
Betul.
Abdul Rauf. Abdul Rauf.
Yes,
Abdul Rauf.
yes, doctor.
Do you understand?
Yeah.
Any question?
In the question, when you asked about the difference between the transfer modeling and the time space modeling, I didn't understand that difference.
Okay. Difference between transfer function model and state space model. Is this what you want?
Yes.
Transfer function state space. So transfer function GS, you have a numerator, denominator. This one is a fraction, am I right? Hello?
Yeah.
It's fraction. For example, 2s s square plus s plus 9. Okay, is a fraction. Single input, single output. Am I right? Hello?
Yeah.
For state space, we have a x dot y. So in matrix form. Brother, matrix form. A, B, C, D. No fraction. And it is a multi-input, multi-output.
Okay.
Can be 3 output, 1 input, 3 output, or 1 input, 2 output, and so on. And did I answer your question?
Yeah.
Shwada? Tak datang? Tak datang Okay. Akil?
Yes, doctor.
Faham? Do you understand?
Doctor.
Do you understand?
Yes, doctor.
Any questions?
No, doctor.
Huh? Ravitran? Ravitran?
Yes, doctor.
Tell us your preparation for Diwali.
So far good, doctor.
So far good.
All okay.
Huh? Any invitations to your classmate?
No, doctor.
Close house. Open house or close house?
Close house, doctor.
Close, huh? Okay, thank you very much, Landry. Okay,
Thank you,
guys,
doctor.
thank you for your attendance today. Okay, those didn't mention the names, I assume attended the class. Our participants today is 56, okay, over 66. 10 is not coming. Omar Abdul Gawad asking for, is there any attendance? Is no attendance. When I call your name, you respond. So meaning that you are attend to the class. But if your name is not called, I assume you're in the class. Okay. So thank you very much. Have a nice weekend. Bye-bye.
Thank you, doctor.
Thank you, doctor.
Thank you, doctor.